In this video, the focus is on the addition of alcohol to an alkene, specifically the acid-catalyzed ether synthesis reaction. The goal here is to predict the major product for the reaction of 1-butene with methanol in the presence of an acid catalyst. Based on this problem, the major product is predicted as follows. The reaction between 1-butene and methanol with an acid catalyst is an addition reaction known as acid-catalyzed ether synthesis. This reaction follows Markovnikov's rule. Therefore, the major product is 2-methoxybutane. The H+ adds to carbon 1, and the methoxy group adds to carbon 2. Since the product, 2-methoxybutane, has a chiral center at the second carbon, the reaction will form a racemic mixture, an equal combination of the 2R, 2-methoxybutane, and 2S, 2-methoxybutane enantiomers, as the major product. The reaction mechanism for the acid-catalyzed addition of alcohol to an alkene proceeds through a carbocation intermediate and involves three main steps. Just a quick note. The acid catalyst ionizes in the methanol solvent to generate the methyloxonium ion, CH₃OH₂+, which is the actual proton donor. For reference, the SO resonance bond order is about 1.67. Step 1. Protonation of the alkene. The reaction begins with the pi electrons of the 1-butene's double bond acting as a nucleophile and attacking the strong acid. A proton is transferred to the alkene. Following Markovnikov's rule, the proton adds to the less substituted carbon atom to form the more stable secondary carbocation at carbon 2. This is the rate-determining step. Note, adding H+ to carbon 1 forms a secondary carbocation, which is much more stable than the primary carbocation that would form from addition to carbon 2. The reaction preferentially proceeds through this more stable intermediate. Step 2. Nucleophilic attack by alcohol. The resulting secondary carbocation intermediate has a planar structure with an empty p orbital on the positively charged carbon C2. A molecule of methanol acts as a nucleophile and attacks the empty p orbital of the planar carbocation at carbon 2 from either the top or bottom face with equal probability. This forms an oxonium ion, a protonated ether intermediate. Step 3. Deprotonation. The final step is the deprotonation of the oxonium ion. Another methanol molecule, or the solvent, acts as a weak base, removing a proton to regenerate the acid catalyst and form the neutral ether product, 2-methoxybutane. The overall reaction is an equilibrium, typically driven toward the ether product by using excess methanol in heating. Let's summarize. Step 1. The alkene is protonated to form the more stable secondary carbocation intermediate, Markovnikov addition of H+. Step 2. An alcohol molecule attacks the planar carbocation from both faces with equal probability. Step 3. Deprotonation yields the neutral ether product, 2-methoxybutane, and regenerates the acid catalyst. Let's organize by keywords. The reaction is acid-catalyzed ether synthesis, where alcohol is the reagent and H+ is the catalyst. The addition follows Markovnikov's rule, prioritizing the formation of the most stable secondary carbocation. The reaction mechanism involves the formation of a carbocation intermediate. Therefore, the final major product is 2-methoxybutane, formed as a racemic mixture of R and S enantiomers. To wrap up, those who wish to deepen their understanding of acid-catalyzed hydration and catalytic hydrogenation are encouraged to study the following topics. If this video was helpful, we'd really appreciate it if you could share it with others. See you in the next reaction.